Imagine a universe just constantly changing. Stars exploding, planets whirling around, stuff reacting chemically in all sorts of ways. Everything's in flux, right? But picture this. Amidst all that chaos, there's this one number, this fundamental quantity that somehow always stays the same. No matter what happens, it's conserved perfectly. Welcome to the Deep Dive.
Yeah.
Today, we're tackling one of the absolute cornerstones of physics, but it's also kind of baffling. The law of conservation of energy.
Yeah, and our plan is to really get under the hood of this idea. We're digging into a real classic here, parts of the Feynman lectures on physics, specifically Volume 1, Chapter 4 on energy conservation. And this isn't about just, spitting out formulas. It's about trying to grasp this really deep, kind of weird fact about how nature actually operates.
Absolutely. By the time we're done with this deep dive, you should have a much better feel for what this law actually means and, importantly, how it pops up everywhere. From simple gadgets to the cosmos itself, it points to this hidden sort of constancy, which is elegant, sure, but also super useful.
It sounds almost too simple, doesn't it? Just one number that doesn't change.
Exactly. But figuring out what that number even is and how we track it, that's where the real meat is. So let's start there. What actually is this energy thing? So, okay, the big idea. What is energy conservation, really? Feynman puts it like this. A certain quantity, which we call energy, that does not change in the manifold changes which nature undergoes, feels almost poetic.
It does a bit, yeah, because at its heart, it's an abstract thing. It's a mathematical principle, a number. It stays the same as things happen. You can't really point to it like a gear turning or something. It's just this numerical fact. Calculate it before, calculate it after, and boom. Same number. And the lectures really stress this. There is no known exception to this law. It is exact so far as we know.
Okay, but if it's not physical, how do we even get a handle on it? It sounds slippery.
Right, and that's where Feynman's genius comes in. He uses this fantastic analogy, Dennis the Menace and his blocks.
Yes, the blocks. Tell us about that.
Okay, so imagine Dennis. He's got 28 identical blocks, and crucially, they're indestructible. His mom counts them every night. For a while, easy peasy, always 28. That's her constant.
Simple enough so far. The conserved quantity is 28 blocks.
Exactly. But then life happens. One day she counts 27. Where's the missing one? Under the rug. So, lesson 1. You have to look everywhere. Just like energy, it might be hidden somewhere or in a different form you weren't expecting.
Makes sense.
What's next? Next day, only 26. Turns out, Dennis left the window open and 2 blocks are outside in the garden. Lesson 2, you got to define your system. If something leaves the system in the room, in this case you need to account for that, energy can flow in or out too.
Okay, so hidden energy, energy leaving the system. What about energy coming in?
Yep, that happens too. One day, she finds 30 blocks. Turns out his friend Bruce visited, brought his blocks, and left a couple behind. So you have to account for energy entering the system from outside. Once she figures all this out, checking everywhere, accounting for ins and outs, she's back to 28 for a while.
Uh-oh. I sense more trouble.
You bet. One day, she counts 25. 3 are missing. She spots Dennis's toy box, but he flat out refuses to let her open it. No looking inside.
So now the blocks are genuinely unseen. How does she handle that? This is where it gets interesting, right?
This is where it gets brilliant and connects directly to energy. She can't see the blocks in the box. But she's smart. She knows each block weighs, say, 3 ounces. She weighs the empty toy box beforehand. Maybe it's 16 ounces. So she comes up with a formula.
A formula for blocks.
Yeah. She says, okay, the total number is the blocks I can see, PLUS. Take the current weight of the box, subtract the empty weight, 16 ounces, and divide that by 3 ounces per block. And lo and behold, even though she can't see inside the box, this calculation always gives her 28. She's found a way to calculate the unseen blocks.
That's really clever. It's an indirect measurement based on a known property of the weight.
Precisely. And then it gets even wilder. Dennis starts chucking blocks into the dirty bathwater. She can't see them at all down there.
Okay, now what? Weighing the bath won't work.
Right. So she adds another term to her formula. She measures the water level. She knows the bath's dimensions and figures out each block raises the water by, say, a 1/4 inch from its normal 6-inch level. So her formula becomes blocks I can see plus weight of box 16.3 plus water level 6 inches, 14 inch per block.
Whoa, that's starting to look like a proper physics equation.
It is. It's a complex calculation she has to perform. But the amazing thing is, no matter what Dennis does, hides them, throws them out, puts them in the box, dunks them in the bath, Her calculated number always comes out the same, 28.
Okay, so the analogy shows how you can track a constant quantity even when it's hidden or transformed using calculations based on measurable effects. How does this map onto energy? What's the big reveal?
The biggest reveal, the most mind-bending part is this. With energy, Feynman says there are no blocks.
Wait, what? No blocks?
No blocks. Energy isn't a thing like a block. It's purely abstract. There's nothing concrete being passed around or hidden under the rug. We just have these various mathematical formulas like the mother's formula for the box weight or the water level that represent different forms of energy.
So like gravitational potential energy or kinetic energy.
Exactly. Gravitational, kinetic, heat, elastic energy in a spring, electrical, chemical, radiant energy like light, nuclear energy, even mass itself through EMC2. Each has its own formula. And the law of conservation of energy is simply the observation that when we calculate all these different forms of energy in a closed system and add them up, the total sum, it just stays constant. It doesn't tell us why the formulas are what they are, just that this total works.
That is pretty profound. It's a purely mathematical observation about nature that holds true everywhere, for everything.
It's incredibly powerful.
Okay, let's dig into one of those forms then.
Yeah.
How about gravitational potential energy? How do we even figure out the formula for that just from basic principles? The text mentions it's kind of like an argument Carnot made for steam engines.
Yes, it's a beautiful piece of reasoning based on one core idea, a hypothesis about the world.
Which is?
Simply this. There is no such thing as perpetual motion.
Ah, the classic impossible machine. So no getting energy for free.
Pretty much. For weightlifting machines, it means you can't have a machine lift a weight, return to its starting condition, and have it ready to lift again without putting some energy in from outside. It can't run forever on its own.
Right. So how does that help us calculate potential energy?
Well, first we need the idea of an ideal machine, a reversible machine. Think of it as perfectly efficient, no friction, no energy wasted as heat. It's theoretical, but it represents the absolute best possible performance.
Okay, the gold standard.
Exactly. Now, imagine you have one of these perfect reversible machines, machine A, and then you have any other machine, machine B. Maybe it's got friction, maybe it's just designed differently. Let's say both machines use 1 pound falling a certain distance to lift 3 pounds. The question is, how high do they lift the 3 pounds?
You'd think the perfect one, machine A, would lift it higher.
Let's reason it out using the no perpetual motion rule. Suppose machine B could lift the weight higher than machine A. Let's say A lifts at height X, and B lifts at height Y, and Y is greater than X.
Okay.
Then you could use machine B to lift the 3 pounds up by height Y. Then you could use machine A in reverse, since it's reversible, to lower the 3 pounds back down by height X. When A runs in reverse, it lifts the original 1 pound weight back up.
Right, so the 3 pound weight ends up slightly higher than where it started, y minus x, and the 1 pound weight is back where it started, and the machine is back to its original state.
Exactly. You've ended up with the 3 pound weight higher than it began with no net energy input. You could repeat this cycle, lifting it higher and higher. That's perpetual motion.
I see. So machine B cannot lift it higher than machine AY cannot be greater than X.
Correct. By the same logic running B in reverse, machine A cannot lift it higher than machine BX, cannot be greater than Y.
Which means they have to lift it to the exact same height. X must equal Y.
Precisely. All reversible machines doing the same job must have the exact same performance, regardless of their internal workings. We can figure out the ideal performance without even looking inside the machine, just based on no perpetual motion.
That's incredibly powerful. So how do we calculate what that height X actually is?
This is where Feynman uses that clever example with the balls on a rack. Picture 3 identical balls sitting on shelves, one above the other, and then one identical ball sitting on a stage. Let's say it's 1 foot off the ground.
Okay, got it set up.
You have your reversible machine connecting the single ball and the rack of 3 balls. First, you roll the single ball off the stage onto the machine's platform that takes no energy. It's horizontal. Then the machine operates. It lowers the single ball by 1 foot to the floor. Using that energy, it lifts the rack with the 3 balls up by some unknown height. Let's call it X.
And the shelves are spaced just right.
Yeah, the shelves are spaced X apart. So after lifting, the bottom ball is now X feet off the ground, the next is 2X, the top one is 3X. You then roll these balls off horizontally onto new platforms. Finally, you return the machine to its original state. What's the net result of the whole process?
Well, the single ball went down 1 foot. The 3 balls effectively got lifted. Let's see. The center of gravity moved up by 2x. No, wait.
Think simpler. Compare the start and end states. One ball is on the floor instead of 1 foot up. 3 balls are now at heights x, 2x, and 3x instead of being on the floor effectively. If we consider lifting one ball by 3x,
Let's rephrase. The machine converted the potential energy of one ball dropping 1 foot into lifting 3 balls by height x. Is the net effect equivalent to lifting one ball by 3x?
that's one way to think about the exchange. More directly, the energy lost by the one ball, weight 1 foot, must equal the energy gained by the 3 balls, 3 weight x, for the process to be possible without perpetual motion.
If the work done lifting the 3 balls, 3 weight x, was more than the energy gotten from the one ball, weight 1 foot, you could run it in reverse and get energy for free.
Exactly. And if it was less, you could run the forward process, then reverse it differently to get perpetual motion. So they must be equal.
So weight 1 foot equals 3. Weight x. The weights cancel out. 1 foot equals 3x, which means x must be 13 of a foot.
Precisely. We deduced the exact lifting height just from the principle. Generalizing this, if a weight W falls a distance h, a reversible machine can use that energy to lift a weight PW, P times the original weight, a distance of HP.
Which leads to the idea that the quantity, weight times height, is what's being conserved or exchanged here.
That's right. And we call that quantity gravitational potential energy, weight times height. And crucially, Feynman notes, it turns out experimentally, in fact, to be true. Theory matches reality.
That's always good. And this idea of potential energy isn't just for gravity, right?
No, it's broader. It's energy something has due to its position or configuration relative to other things, like electrical potential energy based on where charges are. The general idea is that the change in energy equals the force involved multiplied by the distance that force acts over.
And knowing this principle is super useful, right? It bypasses needing to know all the fiddly details of forces sometimes. Like all those pulley and lever rules are just this.
Fundamentally, yes, they are all consequences of energy conservation. Think about an inclined plane, say a 3-4-5 triangle ramp. Put a 1-pound weight on the slope. How much weight hanging vertically over a pulley do you need to balance it?
Normally I'd start drawing force diagrams, breaking vectors down. Cosine.
Cosine. Forget all that. Just use energy. Imagine the 1-pound weight moves 5 feet up along the slope. How much height has it gained vertically?
On a 3-4-5 triangle, if the hypotenuse is 5, the vertical side is 3, so it gained 3 feet in height. Its potential energy increased by 1 pound 3 feet.
Right. Now, for the system to be balanced, or move without acceleration, the balancing weight hanging vertically must have lost that same amount of energy. Since it moved down 5 feet, the same distance the block moved along the slope,
its weight must be W, such that W times 5 feet equals 1 pound times 3 feet. So W equals 35 of a pound.
Exactly. Deduced straight from energy conservation. No force is needed. Much quicker.
That really is a shortcut. The text mentions Stevinus had an even cooler visual proof.
Yeah, the wreath, the spheres on the prism, it's brilliant. Shows equilibrium must happen just by symmetry. But the energy method works for complex things too, like a screw jack.
Okay, how does that work? Let's say a big one. Lifting 1 ton, 2,000 pounds with a screw that has 10 threads per inch, turned by a handle that's 20 inches long. How hard do you have to push the handle?
Again, think energy. To lift the 2,000 pounds by 1 inch, how many times do you have to turn the handle?
10 threads per inch, so 10 full turns.
Right, and each turn, your hand pushing the 20-inch handle travels in a circle. The circumference is 2 pi radius, so 2 pi 20 inches, about 126 inches per turn.
Okay, so 10 turns means my hand moves 1,260 inches.
Now, energy conservation. The work you do, force distance, must equal the work done lifting the weight height. So your force, let's call it F, times 1,260 inches, must equal 2,000 pounds times 1 inch.
So F gives all 2,000, 1,260. Wow, that's only about 1.6 pounds. You can lift a ton with less than 2 pounds of force.
Yep. That's the power of mechanical advantage, explained simply by energy conservation. It works for balancing things, too, like levers.
Like that weighted rod example. An 8-foot rod supported at one end with 60 pounds in the middle at 4 feet and 100 pounds at 2 feet from the support. What force at the far end, 8 feet, balances it?
This uses the principle of virtual work. Imagine the rod tips just a tiny bit. Let's say the far end moves down by an amount we'll call 4 units of distance.
Okay, a virtual displacement.
Because it's a rigid rod pivoted at the end, the middle point at 4 feet, half the length, would move up by half that amount, so 2 units, and the point at 2 feet would move up by a quarter, so 1 unit.
Right, simple ratios.
Now, for the rod to be balanced, the total virtual work done must be 0. Work is force times distance moved in the direction of the force. So the downward force W you apply at the end moves down 4 units. That's a work of maga4W, negative, because force and displacement are in the same direction. Usually we define lifting work as positive. The 60-pound weight moves up 2 units. That's work done against gravity of plus 62. The 100-pound weight moves up 1 unit. Work is plus 101.
So the total virtual work is negative 4W plus 120 plus 100. And for balance, this must be 0.
Exactly. So negative 4W plus 220 equals 0, which means 4W equals 220, so W equals 55 pounds.
Again, figured out just by thinking about energy changes during tiny imagined movement. That's quite versatile.
It's incredibly useful for analyzing structures, bridges, anything in equilibrium.
Okay, let's switch gears. We've talked potential energy. What about the energy of motion? Kinetic energy. The classic example is the pendulum, right?
Perfect example. Pull the pendulum bob to one side. It's high up, not moving for an instant. What energy does it have?
Maximum potential energy, minimum kinetic energy. 0, actually.
Right. Now let it go. It swings down. As it falls, its height decreases.
So its potential energy goes down.
Yeah.
But it's speeding up.
Exactly. That lost potential energy is being converted into kinetic energy, the energy of its motion.
And at the very bottom of the swing.
It's at its lowest point, so minimum potential energy, but it's moving fastest, so maximum kinetic energy.
And that kinetic energy carries it back up the other side, converting back into potential energy as it slows down.
Precisely. It's a continuous trade-off. Potential to kinetic, kinetic back to potential. If there were no friction or air resistance, the total energy, potential plus kinetic, would remain absolutely constant and it would swing forever.
So the total energy is conserved, just swapping forms.
Yeah.
What's the formula for kinetic energy?
It's approximately KE, weight and velocity, to 2g, where g is the acceleration due to gravity. The important thing is that energy is stored in motion itself, separate from gravity.
And you said approximately.
Yes, like the simple potential energy formula, weight height. This kinetic energy formula is an approximation that works well at speeds much less than the speed of light and near the Earth's surface. The exact relativistic formulas are more complex, but the key point is that the total energy, calculated correctly using the exact laws, is always conserved. The principle is exact, even if our simple formulas are approximations.
Got it. So we have gravitational potential energy, kinetic energy. What else is in the energy zoo? You mentioned elastic energy.
Right. Think of stretching a rubber band or compressing a spring. You have to do work to deform it. That work is stored in the material as elastic potential energy.
And when you let go?
The spring snaps back or the rubber band flies. The stored elastic energy converts into kinetic energy. If you just counted potential and kinetic, your energy books wouldn't balance when dealing with springs. You have to include the elastic term.
Okay, makes sense. But, like the pendulum eventually stops swinging, a bouncing spring eventually stops bouncing. Where does the energy go then? It can't just disappear, right?
Right. This was a huge puzzle historically. The answer, heat energy.
Heat? How is that energy?
When the spring stops, or the pendulum stops, the energy hasn't vanished. It's been transferred into the random microscopic jiggling of the atoms within the spring, the pivot, the air around it. This random atomic level motion is energy. It's essentially kinetic energy, but disorganized and at a tiny scale. We perceive this increased atomic jiggling as warmth. We measure it with a thermometer.
So heat is just microscopic kinetic energy.
Wow. Mostly, yes.
Yeah.
And this is why real machines aren't perfectly reversible like our ideal thought experiments. There's always some friction, some air resistance that turns some of the nice organized energy, like the pendulum swing, into this random disorganized heat energy. And getting that heat energy back into useful organized motion is difficult.
That sounds like the laws of thermodynamics starting to creep in.
Exactly. Entropy and the limits on converting heat back to work. But the total energy, including the heat generated, is still conserved.
Amazing. Okay, what other forms are there? You listed quite a few.
Well, there's electrical energy that's related to forces between electric charges, moving electrons through circuits, storing charge in capacitors.
And light.
Radiant energy. Light, radio waves, X-rays, they are all forms of electromagnetic radiation. Feynman describes it as wigglings in the electromagnetic field. Fundamentally, it's a form of electrical energy propagating through space.
Okay. Chemical energy, like in food or fuel.
Yes, that's energy stored in the bonds between atoms and molecules. When a chemical reaction happens, like burning wood, the atoms rearrange into lower energy configurations, releasing the difference, often as heat and light. Modern physics sees this as mostly a combination of the kinetic energy of electrons within the atoms and the electrical potential energy between the electrons and the atomic nuclei.
So chemistry is basically physics underneath. What about deeper inside the atom, nuclear energy?
Right. This energy is associated with the configuration of protons and neutrons inside the nucleus. Processes like nuclear fission, splitting heavy atoms, or fusion, joining light atoms, can release enormous amounts of energy because the particles settle into much lower energy states. It seems distinct from the chemical electrical forces outside the nucleus.
And finally, mass itself, EMC squared.
Einstein's big one, mass energy. It says that mass itself is a form of energy. Just by existing, an object has an intrinsic energy equal to its mass times the speed of light squared. You see this dramatically in particle physics, like when an electron meets its antiparticle positron. They annihilate each other, poof, their mass disappears entirely and is converted into pure radiant energy, like gamma rays. Mass is converted into energy following EMC4.
So the total amount of mass plus energy is conserved, or rather mass is just one more form energy can take.
Precisely. And having this catalog of energy forms, gravitational, kinetic, heat, elastic, electrical, radiant, chemical, nuclear, mass, allows us, as Feynman says, to analyze processes without having to go into the details. We just track the energy balance sheet.
It's like an incredibly powerful accounting system for the universe, a real cheat code.
It really is. And energy isn't the only thing that's conserved. Physics has found several other fundamental conservation laws. The lectures mention 6 key ones in total.
6. Okay, what are the others? Are they as abstract as energy?
3 of them are similarly abstract and deeply connected to the symmetries of space and time.
Go on.
There's conservation of linear momentum. This is related to the fact that the laws of physics are the same everywhere. It makes no difference where in space you do an experiment. Space is uniform.
Okay.
Then there's conservation of angular momentum. This is related to the fact that space is isotropic. It looks the same in all directions. If you rotate your experiment, the laws of physics don't change.
And energy conservation fits in here too.
Yes, conservation of energy is related to the symmetry of time. The laws of physics don't change over time. It makes no difference when you do an experiment. These 3 momentum, angular momentum energy are profound consequences of how space and time work.
Wow. Okay, so those are the 3 subtle ones. What about the other 3? The lectures called them simple.
Relatively speaking, yes. They are much more like counting Dennis's blocks. They feel more concrete.
Like what?
First, conservation of charge. Add up all the positive electric charge, subtract all the negative charge in a closed system. That net number never changes, no matter what reactions happen. You can create particle-antiparticle pairs, but you always create equal amounts of positive and negative charge, so the total stays the same.
Right, just counting pluses and minuses. What else?
Conservation of baryon number. Baryons are heavy particles, like protons and neutrons, the main stuff nuclei are made of. Count the number of baryons going into a reaction, counting antibaryons as meta 1, and the exact same number comes out. You can change protons to neutrons, but you can't just destroy a baryon.
So the heavy building blocks are conserved. Is there one for light particles?
Yep. Conservation of lepton number. Leptons are the light fundamental particles, electrons, muons, tau particles, and their associated neutrinos. Again, count the total number of leptons, with antileptons as -1, before and after any process, and the number is unchanged.
So charge, baryons, leptons, those do feel more like counting discrete things, while energy momentum, angular momentum are more about continuous properties of space and time.
That's a good way to think about it. 6 fundamental rules that, as far as we know, are never broken.
Okay, so energy is always conserved, but there's a catch in practice, isn't there? Something about available energy.
Ah, yes. This is hugely important and often misunderstood. Just because energy is conserved doesn't mean it's always useful or available to do work. Feynman says available energy is another matter.
How so?
Think about the heat energy in the ocean. There's a staggering amount of energy in the random motion of all those water molecules. It's conserved, it's definitely there.
But we can't just, plug the ocean in to run a city.
Exactly. The problem is that it's incredibly disorganized low-grade heat. To extract useful work from it, to herd those random motions into organized motion, you generally have to expend more energy somewhere else, like running a refrigerator to create a cold spot, than you'd get out.
So it's conserved, but not accessible.
Right. This is where the laws of thermodynamics come in, particularly the concept of entropy, which measures disorder. In any real-world process, some energy inevitably gets converted into less useful, more disordered forms, usually heat. Energy is conserved, but its quality, its availability to do work, degrades.
That makes sense. Nature conserves the total amount, but doesn't seem to care if it's useful to us. It just spreads it around.
Precisely. As Feynman puts it, nature spends a lot of it in all directions. Our current energy sources, solar, hydropower from rain, powered by the sun, fossil fuels, ancient stored solar energy, nuclear fuels like uranium, they all tap into processes where energy is becoming available, often starting from a more concentrated form.
So looking ahead, where does that leave us? What are the big prospects based on these principles?
Well, the ultimate source, the one that powers the stars, is nuclear fusion, specifically fusing hydrogen isotopes, like deuterium found in ordinary water.
And the potential there is big.
Mind-bogglingly big. The lecture gives some numbers that are just hard to fathom, like the energy potential in the deuterium from just 10 quarts of water per second could equal all the electrical power generated in the entire United States.
10 quarts. That's like 2.5 gallons per second for the whole U.S.
Or another way he puts it, the energy from about 150 gallons of running water a minute contains enough fusion fuel potential to supply all the energy the U.S. uses today, not just electricity.
That is absolutely staggering. The fuel is basically unlimited in seawater.
The fuel is abundant, yes. The challenge, of course, is the practical engineering, as you hinted earlier. Creating and sustaining the conditions for controlled fusion temperatures hotter than the sun's core, confining the plasma is incredibly difficult. But the physics says the energy is there. Feynman ends that section with a characteristic challenge. It is up to the physicist to figure out how to liberate us from the need for having energy. It can be done. He means finding ways to efficiently tap into these vast reserves.
So let's try to wrap this up. What's the big takeaway for you, the listener, from this deep dive? It seems to me that this law, the conservation of energy, it's this incredibly abstract, purely mathematical idea, not something tangible.
Right, you can't hold it.
Yet its absolute consistency, the fact that this calculated number just always stays the same, lets us understand and predict so much about the physical world, from simple machines to exploding stars.
It's a fundamental constant hiding beneath all the change and complexity, an elegant, powerful truth.
We've seen how figuring out this principle helps make sense of levers, pendulums, heat, chemical reactions, even EMC pot shift. But here's maybe a final thought to chew on. We still don't really know what energy is in some deep, fundamental sense. We know how to calculate it, how it transforms, how it's conserved, but maybe not its ultimate nature.
That's true. It remains, in a way, mysterious. We define it by what it does.
So the question is, does that mystery matter for our future? Could getting a truly deeper, more fundamental understanding of what energy actually is unlock completely new ways to access or use it? Or is the path forward purely about better engineering, getting better at managing the forms and conversions we already understand through principles like fusion?
Theory versus practice.
Does a deeper why unlock new hows? That's a great question. Something to ponder until our next deep dive.